So let us begin with this next chapter, that is dual nature of matter and radiation. This is an interesting chapter. Okay. All right. So let's begin with this. So consider this metal wire. Now, what's there inside the metal wire? So metals are generally made up of atoms, right? So inside atoms there is a nucleus and there are electrons. Okay, we know that. So atoms of metals, they gain sufficient energy from the surrounding at room temperature only, and the electrons in the atoms, they become free. And that's why what happens is, if you consider a piece of metal or wire of metal, there are lots of electrons, they are moving in random directions. Okay, so electrons are free, they are moving in random directions inside the metal surface only, right? So now you might ask, if electrons are free, why don't they come out of metal surface? The reason for that is the electrons are still in a positive potential. Okay, in a positive potential, because see, if an atom loses an electron, the atom will have a positive charge. So there are numerous atoms there, okay, millions of atoms which have a positive charge. So that positive charge of atoms, okay, electrons are surrounded by these atoms, right, which are positive charge, you can call them ions. So that's why the electrons don't have sufficient energy to come out of metal surface. Okay, so electrons are out of the atoms, they are randomly moving inside the metal surface, okay, but they don't have sufficient energy to come out of the metal surface, okay, to overcome the potential barrier due to these positively charged atoms, you can say. So now you can give them this energy in several ways. So what you can do is, see, the electrons, they are moving in the metal surface, okay, the energy that they require, the minimum energy required by electrons to escape from the metal surface, this is known as the work function. Okay, this energy is known as the work function. Now you can give that energy in various ways. So depending upon the way that you provide the energy, the emission of electron from the metal surface, it is defined in that way. Okay, so thermionic emission. So if you heat the metal surface, the electrons may come out of metal surface if they gain sufficient energy. Okay, so thermal energy is imparted to electrons to enable them to come out of the metal. So this emission is known as thermionic emission. So next, what you can do is, you can apply some electric field, right? So when you apply an electric field, that means you have some positive potential, let's say positive potential, so electrons will get attracted by a positive potential. So they might gain sufficient energy if the potential is sufficient. Okay, so this is called as field emission. If you apply some electric field, this is known as field emission. And then there is photoelectric emission. So what you can do is, you can just strike this metal surface with the light, okay, or the electromagnetic waves, you can say. Okay, so when light of suitable frequency illuminates this metal surface, the electrons are emitted. So this is known as photoelectric emission. Okay, is this thing clear, everyone? All right. So after that, let us talk about the Hertz and Lennard's experiment. Okay, so Hertz and Lennard were two physicists who worked on the photoelectric effect. Okay, that is the photoelectric emission of electrons, and they observed some strange things which couldn't be explained by the classical theory of light. Now, what is classical theory of light? So we know that light is made up of waves, and that it is made up of the electromagnetic waves. So this is called as classical wave theory of light. Okay, and we also talked about the Huygens theory, right? So Huygens theory is wave theory of light, and Huygens didn't know what kind of wave light is made up of. So it was proved later by Michael Faraday, Maxwell, that it is made up of the electromagnetic waves, and that is known as the classical electromagnetic wave theory of light. Okay, so there are some observations which couldn't be explained by that theory. Okay, so we'll talk about that. All right, so see, the experimental apparatus of Hertz or Lennard's, it looks something like this. This is the schematic diagram. So this is a glass tube. Okay, this is evacuated glass tube. There is a vacuum inside this glass tube, and here you have a source of light. Okay, so Then there is a quartz window over here so that the light will enter in this tube. Okay, and there is anti-reflecting coating also, so that the light will only enter and it will not get reflected back. Okay, then there is a photosensitive metal plate. So what's that photosensitive metal plate? So here the light will strike on this metal plate. It's photosensitive means then when light strikes, the electrons will come out. Okay, and then you apply some potential difference. So this is known as the cathode. Okay, and this end is known as anode. So you apply some potential difference between these two plates. So some battery is connected over here. Okay, so sometimes this is given negative potential, this one is given positive potential. Sometimes the potential difference between them is zero. Sometimes this one would be given positive potential, this one would be given negative potential. Okay, so we'll talk about that. All right, so the C is the emitter or it is the cathode. Emitter means it will emit electrons. Okay, A is anode or it is also known as collector, right? So now we need to remember one thing, that intensity is inversely proportional to R square. So if you move the source of light away, then what will happen? The intensity will decrease. If you move the source of light closer, then what will happen? The intensity would increase. Okay. So now see, what are the experimental observations of Hertz and Lennartz? So they observed, see this first graph, the photocurrent versus frequency. Now what is photocurrent? See, the electrons will be emitted by this metal plate, then it gets collected by this anode. Okay, the electrons are emitted by the cathode, they get collected by the anode, and then you connect some ammeter to it. Okay, ammeter in this circuit, right? So when you connect an ammeter, it will measure some current. Okay, so that current is called as photocurrent. Why photocurrent? Because the electrons are emitted because of what? This is photoelectric emission. Okay, that means you incident this metal surface with light and electrons come out. So this is photoelectric emission. Okay, so that's why this current is known as photocurrent. So see here, the photocurrent and frequency, the graph between them, it's like this. Okay, that means until certain frequency, certain frequency, there is no photocurrent. Okay, whatever is the intensity of light, whatever is intensity of this light, till the time the frequency is less than this particular frequency called as threshold frequency nu naught, there is no photocurrent. Okay, no matter how much is the intensity, how big is the intensity. Okay, so then after this frequency, what happens? The photocurrent, it gets quickly saturated. Okay, it gets quickly saturated. Here intensity is kept constant. So as you increase the frequency, there is no change in photocurrent. The photocurrent quickly saturates. Okay, see the next graph. Next graph is between the photocurrent and the intensity. So here you fix some frequency greater than this one called as threshold frequency. So if the frequency is greater than the threshold frequency, then the photocurrent is just directly proportional to the intensity. Okay, photocurrent is just directly proportional to the intensity. Okay, this is the second graph, right? Next one. Now next one, to understand next one, now what do we need to do? We need to apply some potential difference here. Now you can see this graph, when potential difference is positive, that means the anode is at higher potential, cathode is at lower potential. Then what happens? As we have seen the last graph, this one, okay, at any frequency greater than nu naught is the threshold frequency, the photocurrent is directly proportional to intensity. That means if you increase the intensity, the current will increase. So what you do is you choose a particular frequency nu greater than nu naught and you just change the intensity. Okay, so you choose intensity I1, I2, I3. I3 is greater than I2 is greater than I1. So obviously you will get more current for larger intensity. Okay, you choose different intensities I1, I2, I3. I3 is greater than I2 is greater than I1. Frequency is constant. Frequency nu is greater than nu naught, right? Nu is greater than nu naught. So we have seen that photocurrent is directly proportional to intensity. So if intensity is greater, the current will be more. So current for I3 is greater than current for I2, and it's greater than current for I1, right? But then now when you apply negative potential to the anode, positive potential to cathode, now what will happen? See, the electrons that are coming out of here of the cathode, they will be opposed by the anode, right? Because you have applied a negative potential there. So they are opposed by the anode, and therefore now what will happen? Their speed will decrease. So now if you crank up the potential difference, that means you increase the potential difference here. So you apply more and more energy to decrease the kinetic energy of electrons. So there will be some point where the electrons will stop. Okay, so that means at some value of the negative potential difference applied to this anode with respect to cathode, the electrons will stop. So that is known as a stopping potential. Okay, that is known as a stopping potential, right? So electrons, they stop at the same potential. Okay, that means current becomes zero. How will you know that electrons have stopped? They are not coming, they are not reaching the anode. The current will become zero. Okay, if some electrons reach the anode, there will be some current flowing through the ammeter connected to this anode, okay, or this side of the circuit, right? So if electrons stop, there will be no current. Okay, this thing is clear, everyone? And the observation here is, no matter how much was the intensity of this light, okay, how bright was the light, how much was the intensity of light, the electrons will stop at same potential difference. That means, so see here, the stopping potential for intensity I1, I2 and I3 is equal. What does it mean? It means that whatever is the intensity of light, how bright is the light, it doesn't matter. If frequency is same, if you don't change the frequency, don't change the color of light, okay, you just change the intensity, then the electrons stop at same negative potential of the anode. Okay, what does it mean? You need to apply same energy to stop electrons, and if you apply same energy to stop electrons, that means electrons have same amount of energy, or these electrons will have slightly different energy. Okay, some electrons will be little bit faster, some will be little bit lesser, but maximum kinetic energy of electrons would be same, because you need to apply the same negative potential over here. Is this thing clear? So if maximum energy of electrons is same, that means the energy that they are getting from light is also same, and it does not depend on the intensity. Okay, if energy you need to apply to stop electrons is same in all three cases for intensity I1, I2, I3, that means energy of electrons does not depend on intensity. Energy the electrons are getting from light does not depend on intensity. Okay, so next what you do is, you keep the intensity same, you change the frequency. That means the brightness is same now, okay, for different frequencies. Okay, so this nu3 is greater than nu2 and it's greater than nu1. So frequencies are different, intensity is same, and then if intensity is same, as you have seen here that photocurrent is directly proportional to intensity. So for different frequencies you get same amount of photocurrent. Okay, if collector potential is positive, okay, if anode potential is positive, then now if you make this make the potential negative, now how much potential difference you need to apply to stop these electrons, it will be different in different cases. Okay, so the stopping potential is different in different cases. See here, the stopping potential is different in different cases. So for nu3 the stopping potential is this much, for nu2 the stopping potential is this much. Okay, for new one the stopping potential is this much, right? So for light having greater frequency, if electrons are incident with the light with greater frequency, then the stopping potential for those electrons is greater. What does it mean? Electrons are moving with more kinetic energy, that's why you need more stopping potential, right? So it means that the energy of electrons increases with the frequency of light. Okay, if you shine this metal surface with a light of higher frequency, then the electrons gain more energy, and that's why the kinetic energy will be more, kinetic energy of electrons will be more, right? So that's why you need more stopping potential to stop those electrons. Okay, so this observation says that the energy of electrons increases with what? It increases with the frequency. Okay, all right. So see, what are the observations? So first one, no photoelectric current is observed till frequency of incident light nu is greater than nu naught. So this was your first graph. Okay, so whatever is the intensity, electrons don't get the required energy. Okay, what does it mean? Unless the frequency hits nu naught, whatever is the intensity, the electrons don't just get the required energy. Okay, so this first graph tells you that energy does not depend on the intensity. Energy of the light does not depend on intensity, or at least energy that electrons gain from light does not depend on the intensity. Okay, second graph says that nu is greater than the threshold frequency. So at a particular frequency of light called as nu naught, the electrons come out of metal surface, right? So if nu is greater than the threshold frequency, after that the current is directly proportional to intensity. That is your second graph. Okay, so now you increase the intensity, current increases means the number of electrons that are coming out per unit time of the metal surface, it increases. This is the second graph, observation from the second graph, right? Then third graph. So what does the third graph say? Again, so you have seen the current is directly proportional to the intensity. We are using I for intensity. Okay, so as the intensity increases and the potential of this anode is positive, then you get more current. You get what? More current. Okay, but if you make the potential difference negative, then what happens? Then frequency is same here and just intensity is different. So for all cases, that is I1, I2 and I3, the electrons stop at the same potential. That means the energy that electrons get from the light is same in all three cases, no matter how much is the intensity, because we require same amount of energy to stop the electrons, same amount of stopping potential to stop the electrons. That means the maximum kinetic energy of electrons is same in all cases, no matter what is the intensity, if frequency is same, right? So that is the third observation. Right? So if nu is equal, V naught is same for all intensities, that means energy of electrons is same. Okay, and observation number 4, if you change the frequency and keep intensity constant, you choose different light, okay, and keep intensity constant, intensity same, then the stopping potential changes. If frequency is more, stopping potential is more. If frequency is less, stopping potential is less. That means electron gain more energy from the light if frequency of light is more, right? So these are the observations so far. So now let's understand what do these observations imply. Okay, so from this graph, what can we understand? Now see, the electrons will have some kinetic energy. Okay, electrons will have some kinetic energy. The maximum kinetic energy of electrons, they will have slightly different kinetic energies. Some will be a little bit slower, some will be a little bit faster, but they will have some kinetic energy. and you are stopping all of them. So that means the maximum kinetic energy of electrons would be equal to what? It would be equal to work done by the stopping potential, work done by the electrostatic potential. Okay, so the maximum kinetic energy of electrons must be equal to what? Work done by the stopping potential to stop electrons. Okay, so the work done by stopping potential is equal to charge on an electron multiplied by the potential difference. Okay, that is the work done by electrostatic potential difference. All right, so therefore we get this formula, Ke max is equal to ev naught, and then Ke max is half of m is mass of electron, multiplied by V max square. What is V max? It's the maximum speed of electrons. Okay, it's the maximum speed of electrons, right? Then the minimum amount of energy required by an electron to come out of a metal surface is known as the work function. It's known as what? Work function, and we will denote it by phi naught. Okay, so just remember that. So now let's talk about the characteristics of photoelectric effect. So the photoelectric effect has the following characteristics. The current I is directly proportional to, so these are just observations. Okay, the current I is directly proportional to the light intensity. Okay, if light intensity is doubled, the current also doubles. Okay, the current appears without delay. So this is important. Current appears without any delay. Photoelectric effect is spontaneous. So light is incident on the photosensitive material and the electrons come out. Okay, it's that fast, right? The electrons are emitted only if light frequency f exceeds the threshold frequency f naught, or we are calling it nu and nu naught. Okay, and the value of threshold frequency depends on the type of metal. So this threshold frequency is different for different metals, okay, from which the cathode is made. So nu naught is different for different metals. Okay, because you can imagine that electrons will be surrounded by different kinds of atoms, different kinds of ions. Okay, and density of those ions in the surrounding will also be different. That's why they will need different amount of energies to come out of different kind of metals. Okay, so that is like a common sense. Okay, all right, so now what do we expect from the wave theory of light? So this is important. What do we expect from the wave theory of light, and how our expectations are not matching with these observations? Okay, so photoelectric effect must not be spontaneous. Why it shouldn't be spontaneous? See here, so suppose this is a wave. Okay, it strikes with an electron. So now the energy of wave is not localized at one place. It's not a particle, it is a wave, right? So some amount of energy is here, some energy is here, some energy is here. So if wave is spread, let's say in 50 kilometers, then the energy of wave is spread in 50 kilometers, right? So if wave strikes with an electron, the electron doesn't immediately get all of its energy. It can't get all of its energy. So the electron has to be illuminated by light for sufficient amount of time so that it gains some energy. It gains sufficient energy to come out of metal surface, and that's why the photoelectric effect must not be spontaneous. Okay, because energy of wave is not localized. This is the first observation, and it doesn't match. It doesn't match with our classical wave theory of light expectation. Okay, our expectation from the wave theory of light. Okay, then there shouldn't be any dependence with the frequency. There shouldn't be any threshold frequency. Why shouldn't be? Why the threshold frequency shouldn't be there? Reason for that is, see, we know that energy or the intensity of light is directly proportional to amplitude square. We have seen this in the wave theory of light. So now if you increase the amplitude, the electrons must get sufficient amount of energy no matter what is the frequency, right? If you increase the amplitude, the electrons must get sufficient amount of energy no matter What is the frequency? Yes, no, this was our another expectation. Okay, whatever is the frequency, brightness is enough, electrons should come out. But that's not happening. Electrons are not coming out before uh, a fixed frequency. Okay, if frequency is less than this much frequency called as threshold frequency, electrons are not coming out. That means they are not gaining sufficient amount of energy. So this is also not matching with our expectation. Okay, and electrons must get required energy if the intensity is increased enough. Okay, so that's the same thing. Okay, so that means using the classical wave theory of light, you cannot explain the photoelectric effect. Okay, you cannot explain the photoelectric effect. Is this thing clear, everyone? So then let us discuss some problems just based upon this much theory. Okay, then we'll come back to the problem of the photoelectric effect. Okay, let's see this one. A source of light is placed at a distance of 50 centimeter from photocell and stopping potential is found to be V naught. If distance between the light source and photocell is made 25 centimeters, the new stopping potential will be. Tell me. You are not changing new. The frequency of light is not changed. Okay, so it's option B. Very good. It's V naught only. Okay. If you change the distance of source, what changes? The intensity changes. Frequency does not change. Okay. So intensity changes. Intensity depends on distance and not the frequency. Not the frequency, and therefore the stopping potential does not change. Okay, stopping potential is independent of intensity. Okay, stopping potential is independent of intensity. Right, so very easy question. Stopping potential is independent of intensity, and by changing the distance you can only change the intensity, right, not the frequency. Okay, and therefore the stopping potential will not change. All right, let's see next one. The photoelectric emission occurs only when incident light has more than certain minimum. Tell me. Power, wavelength, intensity, frequency. Very simple question. All right, so it's option D. Okay, everyone knows this. Okay, let's see next one. In photoelectric emission process from a metal of work function 1.8 eV, the kinetic energy of most energetic electrons is 0.5 electron volts. Okay, what is work function? Work function is minimum amount of energy required by the electrons to come out of metal surface. Okay, so that's work function, the minimum amount of energy required by electrons to come out of the metal surface, right? So in photoelectric emission process from a metal of work function 1.8 electron volt, the kinetic energy of most energetic electrons is 0.5 eV. Okay, electron volts. The corresponding stopping potential is. Okay, so now we know the relation between kinetic energy and stopping potential. Okay, so here actually we have seen this unit earlier also. What is electron volt? 1 electron volt. If 1 electron is accelerated by a potential difference of 1 volt. Okay, so it is energy of electron accelerated by potential difference of 1 volt. And how much that energy would be? So we know that energy would be equal to charge multiplied by potential difference. Okay, charge on an electron is 1.6 multiplied by 10 raised to minus 19 coulombs, and potential difference is 1 volt, and therefore it is equal to what? 1.6 into 10 raised to minus 19 joules. Okay, 1 electron volt is just equal to what? 1.6 into 10 raised to minus 19 joules. So we need to remember this unit. Okay, so then what is kinetic energy? It's 0.5 eV, right? So it's given that Ke is equal to 0.5 eV, and we know that Ke would be equal to what? E multiplied by V naught. We have seen this formula. So this is equal to 0.5 in electron volts, and it's equal to E multiplied by V naught. This is given. So just convert electron volts to joules. How will you convert it? Just multiply it by charge on electron. So 0.5 multiplied by E, we can say, is equal to E times V naught. So that E will get cancelled out. So you will get V naught is equal to 0.5 volts. Right? So that's very simple. It's option C. This is clear. When monochromatic radiation of intensity I falls on a metal surface, the number of photoelectrons and their maximum kinetic energy are N and T respectively. If the intensity of radiation is 2I, the number of emitted electrons and their maximum kinetic energy are respectively. Tell me. When monochromatic radiation of intensity I, option B, 2N and T. Very good, that's correct. Right? So what is intensity? Or what's the relation between current and intensity? Current is number of electrons coming out per unit time, right? Or current is directly proportional to electrons coming out per unit time. Okay? So if you increase the intensity, current will increase. We know that it's directly proportional to current. And that means if you double the intensity, the current will double. Okay? The number of electrons coming out doubles if you double the intensity, and kinetic energy we have seen is independent of the intensity, so that's why it's option B. Right? This is simple. Everyone? Yes, Nikita, Indusha. All right, good. Nikita, okay. Let's see next one. The number of photoelectrons emitted for light of frequency nu higher than threshold frequency is proportional to. Tell me. The number of photoelectrons emitted is proportional to. That means current is proportional to. Tell me. It's very simple. Yes, it's option B. Current is proportional to intensity. Right? Current is proportional to intensity. Very simple. Good. Okay, let's see next one. The figure shows a plot of photocurrent versus the anode potential for a photosensitive surface for three different radiations. Okay, three different radiations. Which one of the following is a correct statement? Which one is correct? Okay, so this is for radiation A, this is for B, this is for C. So curves A and B represent incident radiations of same frequency but different intensities. Is this one correct? That is correct, right? Stopping potential is same, means frequency is same. Okay, stopping potential is same, means frequency is same. Right? You need same potentials to stop the electrons. That means frequency of the light is same. Okay. So then their intensity is different. You come to know that from the positive part of this graph. Okay, when potential is positive. So if current is different, means the intensity is different. So it's option A only. The curves A and B represent incident radiations of same frequency but different intensities. Okay, so it is option A. This is clear. A 5-watt source emits monochromatic light of wavelength 5000 angstrom when placed 0.5 meter away. It liberates photoelectrons from photosensitive metallic surface. When the source is moved to a distance of 1 meter, the number of photoelectrons liberated will be reduced by a factor of. Tell me. Option D. Yeah, that's correct. Correct. So number of electrons, I would say number of electrons, or you can say current, is directly proportional to intensity, right? Current is directly proportional to intensity. So, and intensity is inversely proportional to, that I is inversely proportional to R square. So, okay, because intensity is inversely proportional to R square. So, this number of electrons would be inversely proportional to what? Distance square. Okay, distance of the source square. And then you can just put the values. So, N2 is to N1 would be equal to what? D1 is to D2, or R1 is to R2 square. Okay, inverse proportion, right? That's why this for N2 and N1, N2 in the numerator, N1 in denominator. Here you will have R1 in numerator, R2 in denominator, and you have square of that. Okay, then you put the values. So distance initially was 0.5 meters, then it changes to 1 meter. 0.5 divided by 1 square, okay, or this is 1 by 2, 0.5 is 1 by 2, and you have square of that, so it becomes 1 by 4. So N2 therefore becomes 1/4 of N1. Okay, so it decreases by a factor of 4. That's very simple, right? Simple, not simple? Yes, Selva Kumar.
Sorry, simple only, sir.
Okay, good. Let's see next one. A photoelectric cell is illuminated by a point source of light 1 meter away. When the source is shifted to 2 meter, then, okay, this is similar to last problem, I guess. Each emitted electron carries 1/4 of the initial energy. That's not correct, right? Because you are not changing the source, you are just shifting the source. Number of electrons emitted is half the initial number. Each each emitted electron carries half the initial energy. Again, not correct. Number of electrons emitted is a quarter of the initial number. Yeah, that's correct. No, exactly similar to the last one. Okay, let's see next one. When ultraviolet rays incident on metal plate, then the photoelectric effect does not occur. When ultraviolet rays incident on metal plate, then photoelectric effect does not occur. It occurs by incidence of. It might occur by the incidence of. Question should be like this: might occur, right? There is no guarantee, no? All right, tell me what would be the answer. Photoelectric effect doesn't occur for ultraviolet rays, then it might occur for what kind of rays or waves? Tell me. Option B, X-rays. That's correct. Okay. Why? So energy of the light is not sufficient. That's why the photoelectric effect is not happening. Okay. That means frequency of the light is less than the threshold frequency. Now you need to increase the frequency. So out of these options, you need to just see which kind of light will have more frequency compared to that of ultraviolet rays. So infrared, radio and microwaves have lesser frequency. X-rays have more frequency. Okay, X-rays have more frequency, right? So that's why X-rays is the answer. Okay, because photoelectric effect will happen when frequency is greater than a threshold frequency. Okay, so that's very simple. Okay, let's see next one. A photocell is illuminated by a source of light which is placed at a distance d from the cell the distance becomes d by 2, the number of electrons emitted per second will become 4 times. Okay, so distance is made half, number of electrons emitted would become 4 times. That's simple. The light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. What will be the photoelectric current if the frequency is halved and intensity is doubled? Light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. What will be the photoelectric current if the frequency is halved and intensity is doubled? Tell me. This is from NEET 2020. It's option D. Good. Okay, so nu is equal to 1.5 times of nu naught, the threshold frequency. This is given. So if frequency is halved, that means nu prime is equal to what? It's equal to half of this 1.5 divided by 2 of nu naught. That means 0.75 of nu naught. So if it is 0.75 times of nu naught, so nu prime is less than nu naught. And if frequency is less than the threshold frequency, no photocurrent or no photoelectric emission happens, right? So that's why answer is 0. Okay, that's very simple. This is from NEET 2020. So now let us understand the Einstein's explanation of photoelectric effect. Okay, so see the Einstein's explanation of photoelectric effect. So here Einstein gave a completely different theory of light. Okay, so he says that light is made up of what? It's not made up of waves, it is made up of something like particles. Okay, so which is packets of energy, and they are called as what? They are called as photons. Photons, because photo means light, and the particles or the packets containing light, they are called as photons. Okay, then energy of each packet is equal to what? It is equal to h times nu. Nu is the frequency of light and h is the Planck's constant. Okay, h is Planck's constant. All right, then these photons, packets of energy, or you can call them particles of light. Okay, they have no mass, no rest mass. Okay, or you can just say they are massless, but they carry momentum. So photons carry some momentum and energy. Okay, then intensity of light. So this is an important concept, that intensity of light is directly proportional to the number of photons striking per unit area. Okay, so now, okay, we'll see that intensity of light is directly proportional to what? Number of photons striking per unit area. Okay, then in a collision between an electron and a photon, whole energy of photon is immediately given to an electron, and the photon vanishes. So what is photon? It's just packet of energy. Energy is given to electron. That means the photon disappears. Okay, because it's just energy. So if electron gains that energy, the photon disappears. Okay, so number of photons is not conserved in this collision, right? Okay, so now let's see how does this theory of Einstein explain the photoelectric effect. Okay, so in the photoelectric effect, we have the maximum kinetic energy of electrons. So now suppose light has some energy. Okay, so one photon strikes with one electron, then what will happen? The photon has some energy, so that energy is readily given to the electron. Now electron requires some energy to come out of metal surface. If energy of photon is greater than that energy, then electron will come out and it will also have some kinetic energy. So what can we say? That maximum kinetic energy of electron is equal to the energy given by the photon minus the work function. right? What is work function? Work function is energy required by an electron to come out of metal surface. Okay, you can say that it gains some energy, right? So what is the maximum possible kinetic energy of electron? The kinetic energy of electron is equal to the energy given by photon minus energy required by electron to come out of metal surface. Okay, kinetic energy is equal to energy given minus energy required to come out of metal surface. Whatever is the remaining energy, it is the kinetic energy of electron. Is this thing clear, everyone? Okay, good. So then maximum kinetic energy can be written as half of mv max square. It's equal to energy given by the photon is equal to h nu minus work function is denoted by letter phi naught. Okay, phi 0. All right. So now when nu is equal to nu naught, okay, when the frequency is just sufficient, it is just equal to the frequency of light just equal to the threshold frequency. What will happen? The photocurrent just starts. That means very few electrons will gain sufficient energy, or electrons are gaining just sufficient energy to come out of metal surface. Okay, and they just come out of metal surface and then they get attracted by the anode. Okay, so they don't have their own kinetic energy. They are attracted by the anode, the positive potential on anode, right? So what you can say is the kinetic energy of the electron would be equal to 0. Okay, when nu is equal to nu naught, the kinetic energy of electrons would be equal to what? It will be equal to 0. Okay, so put that in this equation, then what do you get? So if you put nu equals to nu naught, the kinetic energy of electrons is 0. The electron just come out of metal surface and other work is done by, that means why do you get the current? Because they are attracted by the anode, positive potential or anode. Okay, so their own kinetic energy is 0, right? So this is the frequency at which photocurrent just starts. Okay, right? This thing is clear, everyone? Okay, good. So you put nu equals to nu naught, so kinetic energy becomes 0. Okay, so therefore you put 0 over here in this equation and nu naught over here. So then what do you get? 0 is equal to h nu naught minus phi naught. So then phi naught is equal to h nu naught. Okay, you get the relation between the work function and the threshold frequency. How much is the work function? Phi naught is equal to h times nu naught. Okay, good. So then you substitute that back in this equation, okay, here. So you will get half of mv max square is equal to h nu minus h nu naught, or half of mv max square is equal to h times nu minus nu naught. Okay, so this equation or or we'll see that in some other form also. This is called as the Einstein's photoelectric equation. In this form also, it is known as the Einstein's photoelectric equation. You can see that's the same equation, right? So half of mv max square is equal to what? H times nu minus nu naught. Okay, or half of mv max square is equal to h nu minus phi naught. This is the Einstein's photoelectric equation. Okay, so if V naught is the stopping potential, then we know that half of mv max square is equal to ev naught. Okay, half of mv max square is equal to ev naught. So ev naught is equal to h times nu minus nu naught. Okay, h nu minus h nu 0. Then now what you can do is you can substitute that nu is equal to c by lambda, because you know c is the speed of light and it's equal to what? Frequency multiplied by wavelength, nu times lambda. Okay, so what would be nu? Nu is equal to c by lambda. You can substitute that. So you get another form of the equation, that is half of mv max square is equal to hc times 1 by lambda minus 1 by lambda naught. Okay, because sometimes they might just ask the different form of the equation. Okay, and again half of mv max square can be written as E times V naught, and it's equal to Hc times 1 by lambda minus 1 by lambda naught. Okay, now you don't need to separately remember these equations, right? Because this is very clear. Okay, half of mv max square is equal to h times nu minus nu naught. So nu can be written as what? C by lambda. Okay, there is no problem. This is another form of the same equation. All right. So then next, suppose there is one more graph left. Now see this graph. This is the stopping potential versus frequency graph of two different metals. Okay, stopping potential versus frequency graph, and you can see these are straight lines. Okay, this is for metal A, this is for metal B. These are straight lines. They are inclined with this new axis. Okay, horizontal axis at an angle of theta, right? So now this graph can be explained by using the Einstein's equation. Okay, actually all of the graphs can be explained. So okay, let me just explain these graphs using the Einstein's photoelectric model. Okay, Einstein's photon model. Okay, so let me just explain the graphs using the Einstein's model. So see this one, first one. Einstein says that energy of the light, it is equal to what? It is equal to h times nu. Okay, so if nu is not sufficient, I mean nu is less than nu naught, it's very clear that energy of light is not sufficient, right? Because energy is directly proportional to what? It's directly proportional to frequency. So electrons are not getting the sufficient amount of energy to come out of metal surface. That's why they don't come out. That's why the current is equal to 0. Okay, so the first graph is clear. Second graph, this one. Photocurrent is directly proportional to intensity. Okay, photocurrent is directly proportional to intensity. So see here, Einstein says that intensity of light is directly proportional to number of photons striking per unit area. Okay, so if you are increasing the intensity, what does it mean? More number of photons will strike on a particular area. More photons strike, that means there will be more number of photon electron collisions. Okay, that means more photons strike, more electrons will gain sufficient energy to come out of metal surface, and that's why the current will increase. So current is directly proportional to intensity. If intensity increases, means there will be more collisions and more electrons will gain energy to come out of metal surface. Okay, so that explains the second graph. And then the third and fourth graph, so it's very simple again. The intensity, see, if you change the intensity, keep the frequency same, that means you are not changing energy per photon. Energy of all photons is same, so all electrons are gaining same amount of energy. Okay, so now therefore, see, if you increase the intensity, more number of photons will strike the electrons, so more electrons will come out, so current will increase, right? For the same frequency, if you increase the intensity, more photons are striking, more number of electrons, that's why the current is increasing. Okay, but energy per photon is same because frequency is same, and that's why electrons are gaining same amount of energy to therefore the energy required to stop the electrons is also same, and that's why the stopping potential is same. That explains this graph, right? So that's simple. Okay, and next one, when the intensity is same, means same number of photons are striking the electrons, so you gain the same current. Okay, but when frequency is different, intensity is same but the frequency is different, then if frequency is higher, energy per photon is higher, that means energy that each individual electron is gaining from the light, it is higher, so its kinetic energy would be higher. and therefore you will need to apply more potential to stop electrons, right? This thing is clear, everyone? And that's why the stopping potential will increase as you increase the frequency. And then let's see this next graph, fifth graph, okay? That is V naught versus nu, the stopping potential versus frequency. So we have seen in last graph also, the stopping potential is increases if you increase the frequency, but the graph between them is a straight line. It would be different for different metals, okay? So see, you have this equation EV naught is equal to h nu minus h nu 0, right? This is Einstein's photoelectric equation. So you can move E on other side, okay? Move E on other side, you will get V naught is equal to h nu divided by E. And what is h nu naught? It is phi naught, okay? So V naught is equal to h nu by E minus phi naught by E. So compare this with equation of a straight line y equals to mx plus c. You are plotting V naught, the stopping potential, on vertical axis, okay? Then you are plotting nu on the horizontal axis. So your y is V naught, x is nu, okay? So what would be slope of this graph? M is equal to h by e. What would be the slope of graph? M is equal to what? H by e. So no matter what kind of metal you take, the slope of this graph would be just h by e. So there might be a question in NEET that the slope of the stopping potential versus frequency graph, okay, same for all metals, same if work, same for all metals, okay? Then another option, if work function is more, the slope would be more, work function is less, the slope would be less, okay? If intensity is more, the slope is more, something like that, okay? So you need to remember that the slope would be same because h is a constant, e is a constant. That's why the slope would be a constant, because slope of this graph is h by e. This thing is clear, everyone? Okay, good. And then next is the intercept. What is intercept? Point at which x is 0, okay? This line, it will cut the y-axis. Here it is v naught axis. The line cuts over here, so that is the intercept. Now if you compare that with y equals to mx plus c, if you compare this equation, then you get intercept is equal to what? Minus phi naught divided by e. Okay, it's equal to minus phi naught upon e. So it explains this graph too, right? This is clear. So Einstein's theory explains all of the observations of photoelectric effect. Okay, good. So now let us see some numericals based on this. The number of photons per second on an average emitted by a source of monochromatic light of wavelength 600 nanometer when it delivers the power of 3.3 into 10 raised to minus 3 watt will be. Okay, so it delivers a power of 3.3 multiplied by 10 raised to minus 3 watt. We want to find out how many photons will it emit. Okay, so P is equal to what? We know it's energy emitted per unit time, right? So now energy of one photon is h nu. What would be energy of these n photons? Let's call it E prime. So E prime would be equal to n times of h nu. Okay, so power is energy by time. So energy of n photons is n times of h nu divided by your time equals to t. Okay, at t is just 1 second because power is given as energy emitted per second. So t is just 1 second, right? And then the wavelength is given. So we need to convert that nu to c by lambda. Okay, so we have n times of h nu, that is h c by lambda is equal to p, and take t equals to what? T is equal to 1 second. Put that over here. Okay, we want n, So move everything else on other side. So n is equal to, therefore you have n equals to what? P times of lambda divided by hc, and that is, what is power? 3.3 multiplied by 10 raised to minus 3. Lambda is 600 nanometer, 600 multiplied by 10 raised to minus 9, and hc, h is Planck's constant, so that is 6.64 multiplied by 10 raised to minus 34, and c is 3 into 10 raised to 8, speed of light. Okay, so here they mentioned that take Planck's constant as 6.6 into 10 raised to minus 34. Okay, so that it becomes simple for calculations. So you can divide this thing by this thing. So this will be 2, then 600 by 3 is 200, 200 by 2 is 100. So you get roughly 100 times, this is 10 raised to minus 34 plus 8 is minus 26, in numerator it is 10 raised to plus 26, plus 26 minus 9 minus 3, that is minus 12, 26 minus 12 is 14. Okay, that is 10 raised to 16. So the answer to this is 10 raised to 16. Right, this is clear. Okay, very simple question. This is from NEET 2022. Okay, all right, good. Let's see next one. This is from NEET 2023. The work function of cesium, Cs for cesium, potassium and sodium are 2.14 electron volt, 2.30 electron volt and 2.75 electron volts respectively. If incident electromagnetic radiation has an incident energy of 2.20 electron volt, which of the photosensitive surfaces may emit photoelectrons? Tell me. Yeah,
It's option A.
cesium only. So what is the energy of the radiation? 2.20 electron volt. Okay, that's good. Correct. Okay, energy of light must be greater than the work function, right? What does it mean? This is h nu. H nu should be greater than h nu 0, right? This is just same condition in other words, that nu must be greater than nu 0. Okay, energy of light must be greater than work function phi naught. Okay, so work function for first one is 2.14, energy of light is 2.20 electron volts. Okay, energy is greater than this work function, but it's not greater for the second and third case, that is for potassium and sodium. Okay, so answer is CS, right? So that's correct. Very simple. Okay, simple question in last NEET. Let's see what happens this time. All right, let's see next one. The threshold frequency of photosensitive material. This is again from NEET 2022. The threshold frequency of a photosensitive material is nu naught. If the light of frequency 4 nu naught is incident on the metal, maximum kinetic energy of emitted electrons will be. Again, that's very simple. You know the formula. Ke max is equal to what? H nu minus H nu naught, right? So this Ke max is equal to H nu. What is H nu? 4 nu naught minus H nu naught. So just subtract that. So that is 3 times nu naught. That's option D. Very simple, right? Okay, let's see next one. The light rays having photons of energy 4.2 electron volt are falling on a metal surface having work function of 2.2 electron volt. The stopping potential of the surface is. Okay, the light rays having photons of energy 4.2 electron volts. This is very simple. Again, stopping potential. see, you can write EV naught, right? So it should click that which form of the photoelectric equation should we use, right? So here they are asking about stopping potential. We have kinetic energy Ke max is equal to h nu minus h nu 0, and because they are asking about stopping potential, Ke max is equal to EV naught, right? So we should use this equation. EV naught is equal to what? H nu minus h nu 0. Put the values. Or actually we can say this is energy of photons minus phi naught. So put the values here. Okay, so this is 4.2 in electron volts minus 2.2 in electron volts. So the answer would be in electron volts. This is 2 electron volts, and that is E multiplied by, let's say, stopping potential. So that 2 electron volts, if you convert it to joules, that is 2 multiplied by charge on an electron, right? So that is E times V naught. So E gets cancelled out and you get V naught is equal to 2. V naught equals to 2 volts. Again a simple question. Okay, this is clear. Everyone? Okay, good. All right.
Sir,
Yeah, tell me.
sir, the answer is 2 volts now, sir. So it must be option C only, sir.
Oh, yeah, I just saw 2. Sorry. I just saw 2. Answer is 2 volt. That's correct. Oh, they gave one option like this, 2 electron volts. Sorry. It is a 2 volt, definitely. All right. There is one thing that to remember. So now the product of H and nu, sorry, product of H and C. So H times C is equal to 1240 nanometers. Okay, and it is equal to, sorry, what did I say? H times C is equal to 1240 EV nanometers. Okay, H times C would be equal to 1240 EV nanometers or 12,400 EV angstrom. Okay, so this thing we need to remember. The product of H times C is equal to what? It is equal to 1240 EV nanometers, and it's equal to 12,400 EV angstrom units. Okay, this is very important. All right, let's see this one. The work function of photosensitive material is 4 electron volts. The longest wavelength of light that can cause photon emission from the substance is approximately. Tell me. Work function of photosensitive material is 4 electron volts. The longest wavelength of light that can cause photon emission from the substance is. So see, we know that the frequency is equal to c by lambda. That means frequency and wavelength, they are inversely proportional to each other. So if wavelength is longest, that means frequency is shortest. Okay, so longest wavelength corresponds to the threshold frequency, right? Because frequency is minimum frequency for which photoelectric emission happens is the threshold frequency, right? So if frequency is minimum, wavelength would be longest. The longest wavelength for which photoelectric emission happens is the threshold wavelength. Okay, so lambda Yeah, it's option D. Let's check. So nu naught would be equal to what? It's equal to C by lambda naught. So let's check this one. So energy work function is given as 4 eV. Okay. So phi naught is equal to 4 eV, it's given. So that is Hc by lambda naught, right? It's equal to 4 electron volts. And then you can just move that lambda naught on that side. Lambda naught is equal to, you get Hc divided by 4 electron volts. So see that expression, okay? I mean this value, we need to use it here. Otherwise, if we substitute H, we substitute C, then it takes long time to solve this. Okay, then also this thing we need to convert to joules. So we need to substitute charge of electron as an extra thing, right? Okay, so what is Hc? It's 1240. If answers are in nanometers, 1240 eV nanometers divided by 4 eV. So just divide it by that. So is it, yeah, 310, right? 310 nanometers is the answer. It's option D, correct. So this is clear. Okay, good. So you need to remember this thing. It will come handy in lot of problems. All right, let's see next one. When the light of frequency 2 nu naught, where nu naught is the threshold frequency, we know that, is incident on a metal plate, the maximum velocity of electrons emitted is nu1. Okay. When the frequency of incident radiation is increased to 5 nu naught, the maximum velocity of electrons emitted from the source plate, same plate, sorry, not source plate, same plate is nu2, V2, not nu2. The ratio of V1 to V2 is, when the light of frequency 2 nu naught, where nu naught is the threshold frequency, is incident on the metal plate, the maximum velocity of electrons emitted is V1. When the frequency of incident radiation is increased to 5 V naught, 5 nu naught, the maximum velocity of electrons emitted from the same plate is V2. The ratio of V1 to V2 is, this is a simple problem. Okay, you have half of m into V square, let's say just V, okay, in place of V max, is equal to h into nu minus nu naught. Let's use this equation twice, that's it. So you can say half of m into V1 square is equal to h times nu1 minus nu naught, and half of m into V2 square is equal to h times nu2 minus nu naught. Divide the first equation by second. So h gets cancelled, half m gets cancelled. You have V1 by V2 square is equal to nu1 minus nu naught divided by nu2 minus nu naught. And what is nu1? So it is 2 nu naught. 2 nu naught minus nu naught divided by, you have next it is 5 nu naught. 5 nu naught minus nu naught. So this thing is nu naught divided by 4 nu naught, right? Nu naught gets cancelled, so it is 1 by 4. But this is V1 by V2 square, so therefore V1 by V2 is equal to 1 by 2. Yeah, and we want the ratio only, so it is 1 by 2. So it's option A. This is clear? Okay, simple. All right, good. So let's see one more question. Photons with energy 5 electron volt are incident on a cathode. See, in photoelectric cell, the maximum energy of emitted photoelectrons is 2 electron volts. When photons of energy 6 electron volt are incident on C, no photoelectrons will reach the anode if the stopping potential of A relative to C is, tell me. Photons with energy 5 electron volt are incident on a cathode. Maximum energy of photo electrons is 2 electron volt when photons of energy okay, what should be the stopping potential? This is the question. Okay, tell me. Option A. Alright, let's check. Photons of energy 2 electron volt are incident. The maximum energy of emitted photoelectrons is 2 eV. So maximum energy is 2 eV, right? So you have eV naught is equal to h nu minus phi naught. Okay. So maximum energy of electrons is 2 eV, or you can say this is Ke max. So Ke max is equal to h nu minus phi naught. So this is 5. No. Energy of electrons is 2, no? Okay, so this is 2 is equal to energy of light is 5 minus phi naught. So from here you get phi naught, and phi naught is equal to what? 5 minus 2, so that is 3 electron volts. Okay, 3 electron volts. Then you substitute that. So you take second equation, when photons of energy 6 electron volts are incident, no photoelectrons will reach the anode. Okay, so EV naught, you want stopping potential, so EV naught is equal to, you have h nu minus phi naught, right? So this is 6 electron volts, so 6 minus phi naught is what? 3, so this is 3 electron volts, and therefore EV naught is equal to 3 electron volts, that is 3 times E. So stopping potential would be equal to what? 3. That's correct. No, it is minus 3 only. Stopping potential is always negative. Okay, the negative potential that we applied to the anode, okay, is called as stopping potential, and stopping potential is always negative, it's not positive. Okay, so if they say 3, if there were options like 3, 4, 5, 6, then 3 is correct, but 3 and minus 3 is there, then answer should be minus 3 only. Okay, because it's the negative potential that we applied to the anode, right? This is clear. Let's see this one. When a metallic surface is illuminated with radiation of wavelength lambda, the stopping potential is V. If same surface is illuminated with radiation of wavelength 2 lambda, the stopping potential is V by 4. The threshold wavelength of the metallic surface is. So problem is simple, right? Alright, tell me. When a metallic surface is illuminated with radiation of wavelength lambda, stopping potential is V. Okay, so we can write that E times V would be equal to what? It's equal to Hc by lambda, because it is illuminated by wavelength lambda, okay, minus phi naught, and then if same surface is illuminated with radiation of wavelength 2 lambda, the stopping potential becomes V by 4. So this is the first case. Second case, we can write that stopping potential becomes V by 4, so E times V by 4 is equal to Hc by 2 lambda minus phi naught, right? This is your equation 2. Okay, then what we can do is we can substitute this equation 1 into 2, or we can solve them simultaneously, both things are identical. So let's substitute 1 into 2. So if we do that and take this 4 on this side, okay, so I will take that 4 on this side, 4 times Hc by 2 lambda minus phi naught, and what remains on this side is, okay, Ev only, and that is Hc by lambda minus phi naught. Okay, and what we want is the threshold wavelength. So first let's find out what is phi naught, and then we'll get the threshold wavelength. So just multiply this out. So what do we get? So this is 4 times hc by 2 lambda, that means 2 hc by lambda minus 4 pi naught. Okay, and this is hc by lambda minus pi naught. So if we move this thing on this side, that is plus 4 pi naught minus pi naught, that would be 3 pi naught. So 3 pi naught is equal to, this is 2 hc by lambda, and this hc by lambda, if you move it on that side, it would be equal to hc by lambda. So hc by lambda, right? And what is phi naught? So phi naught is, we know it is hc divided by lambda naught. So 3 hc divided by lambda naught is hc by lambda. So hc and hc get cancelled out, and therefore what do we get? We get 3 by lambda naught is equal to lambda, or lambda naught would be equal to what? Take this 3 on that side, it would be equal to 3 lambda, right? This 3 will go in denominator. Okay, 1 by lambda naught is 1 by 3 lambda, that means lambda naught is equal to 3 lambda. So that is option B. Okay, this is clear. Okay, let's see next one. A photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and lambda by 2. Okay, so first we use wavelength lambda, then lambda by 2. If the maximum kinetic energy of emitted photoelectrons in the second case is 3 times that the first case, the work function of the surface of the material is. So again, this is simple. This is simpler than the last one, right? So first you use wavelength lambda, okay, and then lambda by 2. So maximum kinetic energy in the second case is 3 times. In second case is 3 times that of the first case. So you can say Ke1 is equal to what? Hc by lambda minus work function phi naught. In second case, it is Ke2 is Hc by lambda by 2 minus phi naught, right? We are just writing down the Einstein's equation, and this 2 will go in numerator, and this thing can be written as what? Ke2, it's given to be equal to what? 3 times of Ke1. So it is 3 times of Ke1 is equal to 2 times of Hc by lambda minus phi naught. And then you can substitute this Ke1 here. Okay, so substitute Ke1 here. What's Ke1? It is Hc by lambda. Then you have 3 times of that. 3 times of Hc by lambda minus phi naught is equal to 2 Hc by lambda minus phi naught, right? So then multiply this out. So what do you get? Therefore 3 Hc by lambda minus 3 phi naught is equal to 2 Hc by lambda minus phi naught, and then just move this thing on this side and this thing on this side. Okay, so we'll get the answer. So 3 Hc by lambda minus 2 Hc by lambda is just Hc by lambda, and that is equal to 3 phi naught minus phi naught, means 2 phi naught, right? 2 phi naught is equal to Hc by lambda, and therefore what is phi naught? Phi naught is just equal to Hc divided by 2 lambda. Okay, so again a simple problem. Let's see next one. A certain metallic surface is illuminated with monochromatic light of wavelength lambda. The stopping potential for the photoelectric current for this light is 3V0. Stopping potential is 3V0. If the same surface is illuminated with wavelength 2 lambda, the stopping potential is V0. The threshold wavelength for this surface for photoelectric effect is. Okay, so first it is illuminated with the monochromatic light of wavelength lambda. Stopping potential is given to be 3V0. So for first case, so in these kind of problems we just need to write down the Einstein's photoelectric equation. So for the first case, stopping potential is what? 3V0. So you can say E times 3V0 is equal to what? hc by lambda minus phi naught. Okay, but don't write hc by lambda naught at the beginning only. Okay, just write phi naught. Then the stopping potential is 3v naught. The same surface is illuminated with wavelength 2 lambda. Okay, the stopping potential is v naught. So again, then if same surface is illuminated with 2 lambda, stopping potential becomes v naught. So E times v naught is equal to hc divided by 2 lambda minus pi naught, right? Okay, so this is first equation, this is second equation, and then what you can do here is, now you can substitute second into the first one. Okay, you can substitute second into first one, right? Or you can simultaneously solve these equations. I mean, multiply the second equation with 3, then subtract that equation from the first one. So it is identical, right? Okay, so let's substitute this. So what do you get? So this is 3 times of, okay, E v naught, E times v naught, and what's that? hc by 2 lambda minus pi naught. So hc by 2 lambda minus pi naught, and that's equal to hc by lambda minus phi naught, right? So then you want threshold wavelength, that's why you are doing this. Okay, so then this is 3 times hc by 2 lambda, 3 times hc by 2 lambda minus 3 phi naught, and that's equal to hc by lambda minus phi naught. Okay, so then take this on this side, so it will be 3 phi naught plus, okay, it will be positive, so 3 phi naught minus phi naught is 2 phi naught, and take hc by lambda on that side. So what do you get? So it is 3 times hc by 2 lambda, 3 by 2 hc by lambda minus hc by lambda is equal to 2 phi naught, right? If you move this thing on this side, it becomes 2 phi naught. Okay, and this is 3 by 2 minus 1, so that's 1 by 2. 1 by 2 hc by lambda is equal to 2 phi naught. So 2 phi naught is equal to 1 by 2 hc by lambda, and then you can just write phi naught as, okay, let's write phi naught as hc divided by lambda naught, and move this 2 on that side, so that is equal to hc divided by 2 times 2 means 4 lambda. So hc gets cancelled out, so lambda naught is equal to 4 lambda. That's the answer, option D. Lambda naught is equal to 4 lambda, right? It is option D. Let's see next one. When the energy of incident radiation is increased by 20%, okay, the kinetic energy of photoelectrons emitted from a metal surface is increased from this value to this value. So 0.5 eV to 0.8 eV. The work function of the metal is, right? So we want work function in eV only. Okay, so then, so suppose you have first case, when kinetic energy, when the energy of incident radiation is E, let's call it E only. So then you have Ke1 is equal to E minus phi naught. Okay, then it is increased by 20%. So if it is increased by 20%, then what would be the value of E? So I can say E prime would be equal to what? 20% extra. So 120% of E, right? That is 120% means 1.2 times of E. Okay, yes, no? Or what I can say is E by E prime would be equal to 100 divided by 20% extra, so 120. Okay, and if you solve this, then this is take E prime on this side and divide the denominator by 100, so it will become what? 1.2. So move that 1.2 on this side, so you get E prime is equal to what? 1.2 times of E. Okay, so then what happens? You get Ke2 is equal to E prime minus phi naught. Okay, and what is E prime? It is 1.2 times of E minus phi naught. This is Ke2. Ke2. Okay, then what we can do here is, so you can move this phi naught on this side, okay, and substitute that here, or we can multiply this equation with 1.2, right? We can multiply the equation with 1.2 and then subtract the second equation from the first one. Okay, both ways are identical. So let's multiply this one with 1.2, first equation with 1.2. So this thing multiplied with 1.2 and write it down here. So what do I get? 1.2 times of Ke1. Okay, we'll substitute the values, is equal to 1.2 times of E minus 1.2 times of phi naught. Okay, so we have this equation. Ke2 is equal to 1.2 times of E minus phi naught. Okay, and Ke1 is equal to, you have E minus phi naught, so E minus phi naught. So just multiply this second equation with 1.2. Okay, so what we'll do is we'll write this equation like this, and then I will multiply this whole equation with 1.2, 1.2 and 1.2. Then I will subtract this one, so this will become positive, right? So therefore this thing gets cancelled out, 1.2e and 1.2e. 1.2 times of Ke1, 1.2 times of Ke1 minus of Ke2 is equal to, you have phi naught minus 1.2 times of phi naught, right? You have this equation, then put the values. Okay, so this will become what? Minus 0.2 phi naught is equal to, what is Ke1? So it is 0.5, and what is Ke2? It's 0.8. 1.2 multiplied by 0.5 minus 0.8, and this thing is 1.2 times of 5 is 0.5 is what? It's 0.6. This is 0.6 minus 0.8 is minus 0.2 times of phi naught, and this is minus 0.2. Okay, and you have minus 0.2. So if you divide that with this thing, you will get what? Phi naught equals to 1. So I think that should be the answer. Okay, this is correct. Is this correct? Yes, no? Okay, see the next one. For photoelectric emission from certain metal of cutoff frequency is new. For photoelectric emission for photoelectric emission from certain metal, the cutoff frequency is nu if radiation of frequency 2 nu impinges on the metal plate. The maximum possible velocity of the emitted electrons will be, right? So let's see this one. For photoelectric emission from certain metal surface, cutoff frequency is nu. Cutoff frequency is nu. Okay, so this is your nu naught. Nu naught is equal to what? Nu only. And if radiation of frequency 2 nu impinges on the metal plate, okay, so what would be the maximum possible velocity? This is simple. So you have half of m into v max square is equal to what? H times whatever is the frequency, here it's 2 nu, minus h nu naught. But what is nu naught? Nu naught is equal to nu. This is given, right? Cutoff frequency itself is nu. So 2 times h nu minus h nu is just h nu and that is half of m into V max square, and you want V max, so take that half m on other side. 2 goes to the numerator, so it is 2 times h nu divided by m is V max square. Okay, and therefore what is V max? It is just square root of that, 2 times of h nu divided by m. Okay, so it is option A, right? This is simple. Okay, this is clear? Yes, no? All right, it's very simple. Let us see next one. Two radiations of photons energies 1 electron volt and 2.5 electron volt successively illuminate a photosensitive metallic surface of work function 0.5 electron volts. Ratio of maximum speeds of emitted electrons is, okay, the ratio of maximum speeds of emitted electrons is, right? So now you have first case, half of m V max square is equal to what? It is energy of photon E1 minus phi naught, and in second case you can write it is half of m V max square would be equal to what? E2 minus phi naught, right? So let's say KE1 is equal to E1 minus phi naught. E1 is the energy of photons, and KE2 is equal to E2 minus phi naught. Just divide first with second because you want ratio of maximum speeds, right? So that is equal to what? E1 minus phi naught divided by E2 minus phi naught. So E1 is 1 electron volt, okay, minus phi naught is what? 0.5 electron volt, and E2 is 2.5 electron volts, and again phi naught is 0.5 electron volts, and kinetic energy is proportional to, you have, this is half mv square, so it's proportional to v square, and that's why what you can do is instead of placing writing half of mv square, you can just say it's v1 by v2 square, right? So that's equal to, this is 0.5 divided by 2.5 minus 0.5 is 2. 0.5 divided by 2 is 1 by 4, right? 0.5 divided by 2 is 1 by 4. So if v1 by v2 square is 1 by 4, what is v1 by v2? v1 is to v2 is 1 is to 2. Okay, so it is option B. Let's see next one. The threshold frequency for a photosensitive metal is this much. If the light of frequency 8.2 multiplied by 10 raised to 14 Hertz is incident on this metal, the cutoff voltage for the photoelectron emission is nearly. Okay, tell me. Right, so you want cutoff voltage, means you need to use this formula. EV naught is equal to what? And frequency is given, threshold frequency is this much, and frequency of light is this much, right? So h nu minus h nu naught, okay, or h you can take common, it's nu minus nu naught, just substitute values. So what do you get? This is 6.6 multiplied by 10 raised to minus 34 multiplied by 8.2 multiplied by 10 raised to 14 minus 3.3 into 10 raised to 14, and this is E times V naught. You want cutoff voltage only, so V naught would be equal to, take E also on that side, so E is 1.6 multiplied by 10 raised to minus 19. Okay, so we can solve it roughly. So this thing would give us 4, right? Roughly we can say this thing gives us 4 multiplied by 10 raised to minus 34, and this thing is plus 14, so it is 10 raised to minus 20. okay, 10 raised to minus 20 and this minus 19, so it gets cancelled out and what remains is 10 raised to minus 1. Okay, so 10 raised to minus 1, then what remains is 8.2 minus 3.3 will give you what? It's 4.9. okay, so nearly 5 times 4 is 20, so 20 times 10 raised to minus 1 means 2. okay, so it's option B. Check my calculation. okay, tell me. That's correct, right? The potential difference that must be applied to stop the fastest photoelectrons emitted by nickel surface having work function of this much when ultraviolet light of 200 nanometer falls on it must be. okay, so tell me, again it's similar. So you want the stopping potential, right? So it is E times V naught is equal to, and now what's given? Now what's given is the wavelength. okay, wavelength is 200 nanometers. So you have hc by lambda minus phi naught. So then put the values. So what is hc? So phi naught is given in electron volts, right? hc we know it is 1240 ev nanometers. okay, ev nanometers divided by lambda. What's lambda? Lambda is 200 nanometers. Just substitute that. So minus you have work function is 5.01, okay, and that is E times V naught. So if we divide that, what do we get? 2 points, shift this one. So 12.4 divided by 2 is 6.2. 6.2 minus 5.01. 6.2 minus 5.01. That is just 1.19, or nearly you can say 1.2. okay, so 1.2, right? So this will give you 1.2 volts, but stopping potential is always negative, right? So EV naught is 1.2, means V naught is equal to what? It gives you V naught is equal to minus 1.2 volts, because 1.2 is present, minus 1.2 is also present, so the answer would be minus 1.2 volts, because stopping potential is always negative, right? So this is very simple. Okay, let's see next one. When photons of energy h nu fall on when photons of energy h nu fall on an aluminum plate of work function E naught, photoelectrons of maximum kinetic energy K are ejected. okay, if frequency of radiation is doubled, the maximum kinetic energy of ejected photoelectrons will be. So again this is also simple. So earlier maximum kinetic energy was K, right, and that's equal to what? H nu minus phi naught, and what you do is you double the frequency. okay, so frequency is doubled, you get K prime is equal to 2 times of H nu minus phi naught, and then there is nothing. okay, so what we can do is we can just subtract the first equation from the second, right, because this is 2 H nu, this is H nu. So let's subtract. Let's take this equation down and subtract it. So this becomes minus minus plus, and therefore you get K prime minus K is equal to H nu, and this phi naught and phi naught will get cancelled, so take K on that side and you get the answer. So K plus H nu, right? So that is the answer. It's option A. It's very simple, right? Okay, let's see this one. A photosensitive metallic surface has work function H nu naught. If photons of energy 2 H nu naught fall on this surface, electrons come out with maximum velocity of this much. When photons of energy is photon energy is increased to 5 h nu naught, then the maximum velocity of photoelectrons will be? Tell me. This is very simple. Yes, what would be the answer? Work function is h nu naught. Photon's energy is 2 h nu naught first. Then you have some kinetic energy. Ke1 is equal to, you can say 2 h nu naught minus work function, that is h nu naught, and then you increase the energy of photons to 5 h nu naught. So 5 h nu naught minus h nu naught would be equal to Ke2, right? We want to compare the maximum velocities, but let's solve this first. Then we can divide this one with this one. So what do we get? So on left hand side you will have v1 by v2 square, and on right hand side you have, this is first of all h nu naught will get cancelled out, and this is 2 minus 1, so that's 1. 5 minus 1 is 4, so this is 1 by 4. That's it. So you have v2 just equal to what? Take square root of this thing, so that thing is 1 by 2. So that's v1 by v2 is 1 by 2. So v2 is just equal to 2 times of v1. So v2 is just 2 times of v1, and that is equal to, so 2 times of 4 into 10 raised to 4 multiplied by 10 raised to 6 plus 6. So it is 8 multiplied by 10 raised to 6 meters per second. Right, so that's the answer. It's option C. Okay, it's very simple. There is nothing in this question, right? Okay, good. Let's see next one. According to the Einstein's photoelectric equation, the graph between the kinetic energy of photoelectrons ejected and frequency of incident radiation is? Tell me which one is correct. This one, this one, this one, or this one? Option D. Okay, everyone, that was asked twice. Option D. Okay, very good. Right, so Ke is equal to what? It is equal to h times nu minus phi naught. Okay, so for K equals to 0, you have nu equals to what? For K equals to 0, you will have nu equals to, put this thing is equal to 0, so h nu minus phi naught is 0, then h nu is equal to phi naught, so nu is equal to what? Phi naught by h. Okay, or you can just say nu is equal to nu naught. For that the K is equal to 0, right? Phi naught by h means it's nu naught only. Okay, so it is some positive value. Okay, so for some positive value of frequency, kinetic energy is 0, and then it will linearly increase. Kinetic energy will linearly increase with the frequency. So that is simple. It's option D. Okay, so before this experiment called photoelectric effect, we used to believe that light is made up of electromagnetic waves. Okay, so see, dual nature of radiation, what's that? So some phenomenon like interference, diffraction, polarization can be explained by wave nature of light. Okay, and in this chapter we have seen in the photoelectric effect, the photoelectric effect cannot be explained using the wave nature of light. You need to think of light as particles or packets of energy, right? Okay, called as photons. But now, is the photon nature sufficient? It is not sufficient. Okay, right? Because using this nature you cannot explain the interference, diffraction, polarization, etc. And that's why both natures of light, that is the particle nature and the wave nature, are important, equally important. So now our current understanding is that light is, so what is light? So answer to this question depends on what you are using to probe light. Okay, so if your experiment involves interaction with waves, then light will behave like waves, and if your experiment involves interaction with particles, then it will behave like particles. Okay, so light shows both natures, the wave nature as well as particle nature. Okay, right. So this is our current understanding. Now we understand that light shows dual nature, the particle nature as well as wave nature. So then next, let's understand de Broglie hypothesis. Okay, some people call it de Broglie. Okay, but it's not de Broglie, it is de Broglie. So what is de Broglie hypothesis? So then next, let's talk about the matter waves. That is the wave particle duality, right? Wave particle duality. So what's this? So de Broglie was a physicist and he hypothesized. I mean, he gave us a hypothesis. So according to de Broglie, the nature is symmetric if radiation, which was well established wave, can show the particle nature, then there should be no bias. The particles should also be able to show the wave nature, right? If radiations, which are waves, it was established by the Michael Faraday and Maxwell, that light is made up of electromagnetic waves. So if they can show, or not they, if light can show the particle nature, okay, that is waves can show particle nature, then particles like electrons, etc., whatever particles, they also show, okay, according to de Broglie, they also show what? They also show the wave nature. Okay, because nature should be symmetric, there should be no bias. Okay, so he gave us hypothesis, as wave behave like material particles, similarly matter must behave like waves. Okay, and there is a wave associated with a moving particle, and the wavelength of that wave, which is known as the wave associated with moving particles, is known as matter waves. Okay, matter wave, and its wavelength is given by h by p. Its wavelength is given by what? H is the Planck's constant, p is the p is the momentum. Okay, so lambda is wavelength of matter waves, it is given by h by p. Okay, p is the momentum, right? So now we need to remember this thing. Okay, so where did it come from? The answer to that is, now if you think about Einstein's mass energy relation, so E is equal to mc square. Okay, and you have energy of a photon. So what is energy of photon? So E is equal to hc by lambda is equal to mc square. Okay, then cancel out this c with this one, so you get h by lambda is equal to m times c. So this is nothing but the momentum of photon. Okay, momentum of photon, right? So that is p. So you move it on this side, then what do you get? So lambda, the wavelength of photon, can be written as what? H by p. Okay, wavelength of photon can be written as h by p. So just like this is the relation between wavelength of photon and momentum of photon, right? So just like that, a particle having momentum equal to p must show there must be a wave associated with that particle called as matter wave, and the wavelength of that wave is lambda. Okay, lambda is equal to what? H by p, right? Is this thing clear, everyone? Okay, good. So now this equation itself shows the dual nature of radiation as well as matter. So momentum, we associate momentum with particles, right? So moving particles have some mass, some velocity, so they have some momentum. Okay, their momentum is what? Mass times velocity. And wavelength is associated with what? It is associated with waves. Okay, so this is connection between the two natures, right? The wave nature and particle nature of matter as well as radiation. Okay, all right. So this equation shows the duality of matter as well as radiation. Okay. Alright, so we have lambda equals to h by p. After that, next we have if a charged particle is accelerated through a potential difference of v, then what would be its wavelength? Okay, so charged particle is accelerated through a potential difference of v, then what would be its wavelength? Okay, what would be the wavelength of matter wave uh, of that particle? So we have kinetic energy of the particle would be equal to what? The potential energy used to charge that particle. Sorry, not to charge the particle. So kinetic energy of particle would be equal to what? Potential energy used to accelerate the particle. Okay, so kinetic energy is p square by 2m, right? It's half of mv square, and it can also be written as p square by 2m. So you have p square by 2m equals to q multiplied by v. Q is the charge on particle, v is the potential difference. Then take that 2m on this side, so you get p is equal to, its momentum is equal to square root of 2m qv. Okay, square root of 2m qv, and then you can easily find out its wavelength. So lambda equals to h by mv, or h by p, and what is p? So it is square root of 2m qv. So you have h divided by square root of 2m qv, right? So we need to remember this formula, okay, or otherwise we'll need to find it out if there is a question based upon this. Okay, so better to remember lambda is equal to what? H divided by square root of 2m qv if it is accelerated by potential difference of v. Right, this is clear, everyone? Okay, good. So then there was Davis and Germer experiment. This topic is deleted from the syllabus. Okay, so we'll not talk about that. So now, if electron is accelerated by, see, we'll take this formula, and in place of the mass of particle, we'll put mass of electron. Charge on the particle, will put charge on electron, right? So if electron is accelerated by a potential difference of v, what would be its wavelength? Okay, so its wavelength turns out to be equal to 12.27 divided by root of v angstrom unit. Okay, and this wavelength, by the way, this wavelength is known as de Broglie wavelength. Okay, because this is de Broglie's hypothesis. Okay, this is a de Broglie wavelength. De Broglie wavelength is equal to this thing. Lambda is equal to 12.27 divided by root of v angstrom unit. So we just need to remember this formula separately for electrons. Okay, because there have been questions based upon this. So lambda is equal to 12.27 divided by root of v angstrom units, right? And by the way, there was an experiment called as Davis and Germer experiment, which confirmed the dual nature of matter. Okay, so in this experiment, what they did was, so what was established? So suppose these are electrons coming this way, these are electrons, okay, electrons, they get reflected from here, suppose, okay, from different planes. So then there would be some part difference between electrons, and then what you see here is the diffraction pattern. Okay, something like diffraction pattern. So diffraction pattern is reserved to what? Waves only, but electrons also show diffraction pattern, means electrons show wave nature. That's it. Okay, so Davis and Germer experiment in nutshell. Okay, so it was confirmed by this experiment. All right, let's see this one. The minimum wavelength of X-rays produced by an electron accelerated through a potential difference of V volts is proportional to. Tell me which one is correct? Yeah, option C. Very good. Very simple question, right? Okay, so this was from NEET 2023 only. Let's see next one. An electron is accelerated from rest through a potential difference of V volts. If the de Broglie wavelength of electron is 1.227 multiplied by 10 raised to minus 2 nanometers, the potential difference is. So de Broglie wavelength is given, and we know that lambda is equal to 12.27 angstrom divided by root of V, and wavelength is also given. So let's move this root V on this side. So this is 12.27 multiplied by 10 raised to minus 10. Okay, you got the answer. Good. And lambda is what? 1.227. 1.227 multiplied by 10 raised to minus 2. But that is in nanometers. So multiplied by 10 raised to minus 9. Right. This is 10 raised to minus 11. Okay. This is 10 raised to minus 11. Move that to the numerator, so it becomes 10 raised to plus 11. Plus 11 minus 10 is 10 raised to 10. Okay, so it is like this thing divided by this thing will give you 10, and this is also 10 raised to 1, so this is 100, right? So then root V is 100, so this thing is 10 raised to 4. I'm sorry, V is equal to 10 raised to 4. So that was the answer, Selva Kumar.
Yes, sir.
Okay, so 10 raised to 4 volts, right? This is very simple. Okay, this is from NEET 2020, and the question based on this has been asked many times. Okay, all right, let's see next one. An electron is accelerated through a potential difference of 10,000 volts. Its de Broglie wavelength is, again same. Okay, simple question. This is from NEET 2019. Okay, so NEET 2019, NEET 2020, same question, right? So lambda equals to you have 12.27 multiplied by 10 raised to minus 10, right? Because they have given the powers here. Okay, one answer is in nanometers. Let's check. And it is 10,000 volts, means 10,000 volts means what? 10 raised to 10 raised to 4 only. Okay, so this thing divided by root of 10 raised to 4, so that's 10 raised to 2. 10 raised to 2 in numerator becomes 10 raised to minus 2. 10 raised to minus 10 minus 2, that is 10 raised to minus 12. So it is option C. Okay, so it's 12.2 multiplied by 10 raised to minus 12 meters. Option C. Right, very simple. There is nothing in the question. So the de Broglie wavelength of neutron in thermal equilibrium with heavy water, okay, at temperature T. So now it might be thermal equilibrium with heavy water or anything else, right? But important thing is the temperature is T. Then you can treat a neutron like an atom. Okay, neutron is just like an atom, or if you have hydrogen atom, you remove an electron from it, what remains is a neutron, right? So it's like an atom only. Okay, so it will have kinetic energy, that neutron will have kinetic energy. K is equal to what? It's equal to 3 by 2 kBt. Okay, kb is the Boltzmann constant, right? We remember this from kinetic theory of gases. Okay, so this neutron is just like an atom. Okay, so then kinetic energy can be written as p square by 2m, and that is equal to 3 by 2. Let's write k only for kb. Okay, kt, 2 gets cancelled, move m on that side, so you get p square is equal to 3 times mkt. Okay, and then therefore what is p? P is square root of 3 mkt, and therefore you have its de Broglie wavelength lambda equals to h by p, that is h divided by square root of 3 mkt, right? This is clear. It's option A, right? So simple, very simple. Of course, if we know this, okay, good. All right, let's see next one. An electron of mass m and a photon have same energy E. The ratio of de Broglie wavelengths associated with them is, okay. So electrons mass is m and photon, they have same energy, okay. So for a photon, you can say E is equal to what? It is h nu, that is hc by lambda, okay. So let's write this for photon. E is equal to hc by lambda p, okay. This is for photon, right? We have studied this. The ratio of de Broglie wavelengths. So for a photon, E is equal to hc by lambda p. And then for an electron, what do you have? For an electron, electron's energy is also same. So electron's energy, you can write p square by 2m for the electron is equal to, it's equal to what? Its kinetic energy. This is its kinetic energy. E is equal to p square by 2m, okay. And therefore what would be its momentum? So p square is 2me, and so you have p equals to square root of 2me, okay. Then you can easily find its de Broglie wavelength. So lambda of electron would be equal to what? So it is h divided by square root of 2me, right? And what would be lambda of photon? So just move this e on other side. Lambda of photon is equal to hc divided by e, okay. So you want electron to photon or photon to electron? Electron to photon, right? We want ratio of wavelength of electron to wavelength of photon. So just divide this, okay. Then we get lambda of electron divided by lambda for photon is equal to HH will get cancelled, right? Or let's write this religiously. Lambda, sorry, H divided by 2me multiplied by, you have E by HC, okay. So HH will get cancelled, HH will get cancelled, and then you have HE by HP, sorry, why am I saying H? Lambda E by lambda P is equal to E divided by this thing, okay. So do you need to move that in square root everything? C is outside, C is outside, so let's keep C outside, move E inside the root, so that is equal to, then move E inside the root, so it will be E square divided by 2me, and they have written it raised to half, right, for square root. Then this thing gets cancelled out, so you have E by 2m raised to half, and there is C in the denominator times 1 by C. It's 1 by C times of E by 2m raised to half, okay. So that is option C, right? Okay, this is clear, everyone. Light of wavelength 500 nanometer is incident on a metal with work function of 2.28 electron volts. The de Broglie wavelength of emitted electron is, okay. Yeah, so you will find out kinetic energy, right? Light of wavelength 500 nanometer is incident on a metal with work function of this much, 2.28 electron volts. The de Broglie wavelength of emitted electron is, simple. So just find out kinetic energy, and that is what? It is energy of a photon, okay. So its wavelength is given, that means hc by lambda minus work function is phi naught, okay. So put the values. What is hc? This is given in nanometers, so we'll make use of 1240 ev nanometer, okay. hc is 1240 ev nanometer divided by, that is lambda equals to 500 nanometers minus phi naught is 2.28 electron volts. So what will be this thing? what I will do is I will multiply numerator and denominator by 2. So this is 1000, then this becomes 1000, right? And this will become what? 248 0 2480, and if I divide that by 1000, so it's 2.48. So 2.48 minus 2.28 electron volts, okay, that is 0.2 electron volts, but then 0.2 eV, and you have electron. Okay, so this thing can be written as p square by 2m. So this is kinetic energy of electron, and it can be written as E times V naught, right? V naught is the stopping potential. So if you need the stopping potential of V naught, right, to stop the electron, that means its kinetic energy must be equal to what? As if you can think as if it is accelerated by a potential difference of V naught. Okay, is this thing clear? Yes, no? Okay, and then you can just make use of lambda equals to 12.27 divided by square root of V, and in place of V we'll just put V naught. Okay, so that's 12.27 divided by root of 0.2, right? But what is square root of 0.2? So you can write this thing as 2 or 20 multiplied by 10 raised to minus 2 root of 20, so it's 4 point something. Okay, let's take 4.5. 4.5 multiplied by 10 raised to minus 1, take that 10 raised to minus 1 into the numerator, it becomes 10 raised to plus 1. Okay, 10 raised to 1, so this thing divided by 4.5, so nearly 3 into 10 raised to 1, 3 multiplied by 10 raised to 1 angstrom. Okay, so that is equal to, so it's 2.8 multiplied by something. Okay, so 3 multiplied by 10 raised to what? This is angstrom is 10 raised to minus 10, so this thing is 10 raised to minus 9 meters, or 3 into 10, sorry, 3 into 10 raised to minus 9 meters is 3 nanometers, right? So this is very round figure calculation. Okay, so now should it be less than or greater than that? So the answer is option D or option A. Tell me. It is accelerated by a potential difference of, and this was maximum kinetic energy. Okay, that means velocity is maximum. If velocity is maximum means the wavelength is, that is the minimum wavelength. Okay, so that should be greater than or equal to, so it's option A. Is this thing clear, everyone? Then which of the following figures represent the variation of particle momentum and associated de Broglie wavelength? Tell me, which of the following figures represent variation of particle momentum and associated de Broglie wavelength? Yes, which one is correct? So option D. That's very simple, right? It's very simple. That lambda equals to, you have h by p, p is inversely proportional to lambda. That's why option D. Okay, good. Let's see next one. The kinetic energy of particle is increased to 16 times its previous value. The percentage change in the de Broglie wavelength of the particle is, tell me. Kinetic energy is increased to 16 times the previous value. Percentage change in the de Broglie wavelength. Okay, so Ke prime is to Ke is equal to 16, right? So P prime, this is okay, or let's take Ke2 is to Ke1 is equal to 16, Okay, so P2 square by P1 square, because kinetic energy is directly proportional to momentum square. So this is 16. That means P2 by P1 is equal to what? 4. Okay, so if P2 by P1 is 4 or 4 is to 1, I can say, then what would be wavelength? So the wavelength is inversely proportional to P. Wavelength is equal to H by P. It's inversely proportional to P. So if momentum becomes 4 times, wavelength will become what? 1/4. Okay. Therefore, you have lambda 2 is to lambda 1 is equal to what? It's equal to P1 is to P2. That's 1/4. 1/4 means how many percent? How much a percent? It becomes 25%, but that's not what they asked. The percentage change in the de Broglie wavelength. Okay, so what's the answer? Tell me. 75%, right? It's option B. Okay, it becomes 1/4 means lambda 2 is 25% of lambda 1, right? But if it is 25%, how much is the change? Change is 75%, right? Change is 75%. Good. Let's see next one. The wavelength lambda e of electron and lambda p of photon of same energy E are related by. Tell me. Actually, we had seen this. Energy is same. Okay, so energy of photon is equal to energy of an electron. So we can put the formula in terms of wavelength. So it is hc by lambda p is equal to energy of electron can be written as what? P square by 2 times its mass, right? And p is inversely proportional to lambda. P is equal to h by lambda. Okay, so let's put that. So you get h square by lambda of electron square times 2 times m, and this is hc by lambda p. Okay, then this h gets cancelled out with the square, right? And you can write this thing as hp is equal to lambda e square times 2 times m into c divided by h. But all this is constant, right? All this is constant. So what you can say is lambda p is proportional to lambda of electrons square, right? Lambda p is proportional to lambda of electron square. It's option C. Okay, this is clear. Let's see next one. If the momentum of an electron is changed by p, then de Broglie wavelength associated with it changes by 0.5%. The initial momentum of electron will be. Okay, this is very simple. See, you have lambda equals to what? H by p. You have this formula, and what you are doing is changing the momentum of electron by p. Okay, the momentum of electron is changed by p. Then its de Broglie wavelength changes by 0.5%. So here you can make use of again the first chapter, the delta lambda by lambda, right? Delta lambda by lambda is equal to what? It is equal to minus of delta p by p, because lambda is equal to some constant, that is h times p raised to minus 1, and that's why delta lambda by lambda is equal to minus of delta p by p, right? But then this change is 0.5%, so they are not saying increasing, decreasing, they are just saying that wavelength changes by 0.5%. So 0.5, okay, times of in denominator, what you can do is you can put wavelength equals to 100 only. Okay, so then what will be delta lambda? It will be 0.5 times of lambda, right? 0.5 times of 100. Okay. Oh no, what did I say? All right, so let's do one thing. So this is delta lambda by lambda times 100 would be equal to minus delta p by p times 100. Okay, and this thing is equal to 0.5, right? Percentage change is 0.5. This is equal to 0.5, and then okay, but they are saying that momentum of electron is changed by p. So let's call the initial momentum as p naught. Okay, initial momentum as p naught, and change in momentum is delta p, so that you can call p then. Okay, so that's equal to p by p naught times 100 is equal to 0.5, and then you can move this thing on this side. Okay, so therefore what will you get? That initial momentum p naught is equal to 100 by 0.5 times of p. Okay, you can forget about the negative sign because they are just giving the magnitude, right? 100 by 0.5 is 200, so it's 200 times of p. This is clear? Yes, no? It's option A. Okay, everyone? Nikita, is it clear? All right, good, good. Let's see next one. Which one among the following shows particle nature of light? Tell me. Photoelectric effect. Yeah, photoelectric effect shows the particle nature of light. Good. And that's it. Okay.